Welcome and hello. This is a HEC ResSim exercise. And in this exercise, we're going to be dealing with state variables and specifically doing an exercise that involves water quality, specifically water temperature. What I have on the screen right now is ResSim. I'm actually using version 3.5 now. I'm going to start by going up to New Watershed and then I'll just call it Project. Click on the location button to navigate to my particular project directory where I want the project directory to go, which is right here, English units. Let's go with the Pacific time zone and oops, wrong one. Pacific, apply, and okay. All right, so we're good to go. Water temperature is one of those water quality parameters that water modelers and reservoir operators need to be aware of sometimes if there happen to be certain downstream water quality requirements, such as minimum water temperature. So we're going to devise and come up with some state variables and keep track of water temperature in this exercise. All right, so from the beginning, let's sketch in our stream alignment. If you're not already on the watershed setup module, go ahead and select that. Of course, you sort of needed to be on this tab to create a new watershed anyway, so sorry for not mentioning that earlier. I'm going to click on the stream alignment tool and then hold down the control key, single left click, continue holding down the control key, and then just kind of sketch out a little bit of a curvature to the stream alignment. Finally, let go of the control key and one final single left click. We'll just call this River A. I'm going to add a computation point by clicking the computation point tool, hold down control, and then a single left click. I'll call that CP1. Next, I'm going to sketch in my reservoir. So we were sketching in the upstream to downstream direction with the stream alignment. Same thing when we're adding reaches or reservoirs. I'll click on reservoir, hold down control, single left click, let go of control, single left click further downstream where we want the dam face to be located. I'm just going to call this reservoir A, res A. And then just for good measure, let's add one more computation point at the bottom of the stream alignment. I'll call that CP4. Okay. I'm going to also add a configuration. So configuration new, I'll just be generic and call it config1. This is going to be the only configuration for this exercise. So you can just pick up a date and then apply and OK. So our config1 is now in the model, in the watershed. And we can also confirm that by going up to configuration editor, and sure enough, config1 has our reservoir A project. All right, I'm going to save the watershed, and then that's all we need to do here in the watershed setup module. Next, I'm going to click on reservoir network. This is where a lot of the work gets done for creating the network. Network new, and I'm going to give the network a name. Network 1. It's going to be based on that configuration 1, config 1, and then click new. All right, so we have our what are now junctions, our reservoir. I'm going to click on the reach tool here and then hold down control, single left click, let go of control, single left click on the next downstream junction. This creates a reach, and then I'll just use their default suggested reach name here. Same thing with the reach between CP3 and CP4. Okay, I'm going to click on the junction tool and then right click to add some local inflow for this CP1 junction and click on local inflow. And in the first line, I'll just type CP1 and inflow with a factor of 1. Let me see if this is one of those dialog boxes I can resize. Nope, looks like I can't. In the bottom right down here, there is an apply button, and then click OK. And I'm going to just turn off the grid lines as well. There we go. All right, let's go ahead and make some edits to our reservoir now. So I'm going to click on the reservoir tool, or even the pointer tool would work. Right click on the element you want to make edits to, edit reservoir properties. Under reservoir, I'm going to change the name from dam river A to just dam. We only have one river downstream of the dam, so that doesn't need to be specific. For the pool geometry, I'm going to just paste in my geometry right here. You can pause the video and use my numbers if you want. Basically, the bottom of the reservoir is at 1350, the top is 1500, with a maximum storage of 100,000 acre feet. All right, and then if I click on dam, then I can define a top of dam elevation. We'll say the top of dam length is 200 feet. And then now I want to add some structures to the dam face, specifically outlets. So I'm going to go right click on dam and then add a controlled outlet. I'm going to say there's 2 gates And then I need to define the elevation versus max capacity relationship for each individual gate. Times 2 gives me the total capacity. As you notice, the invert is 1400. So what I'm going to do specifically is just rename this controlled outlet. So it says CO1 underscore 1400. So it sort of matches the controlled outlet group 1 invert of 1400. I'm going to add another controlled outlet group, just similar to the first one. Right click, controlled outlet. This time it's going to have a higher invert. So I'm going to rename it CO2 underscore 1450, which, as you may presume, it will have an invert of 1450. I'm going to paste those numbers in here and then change it so there's also 2 gates. All right, just for good measure, I'm going to add an uncontrolled outlet at the very top of the dam. So that will have an invert of 1490. Here are the numbers there. And I think that's all I have to do. I'm going to come down here to the bottom right and click on Apply. And then if I click on Dam here, we can see the combined max capacity for each elevation for controlled, uncontrolled, and then total, which is summarized in this little plot right here with blue being controlled, red being uncontrolled, and green line being total. Over in the Operations tab, this is where we create the operation set 1. And then we have 3 zones by default. I'll just go ahead and use these zones that it's providing me. The top elevation I'll say is 1500. So that's a constant year-long 1500 top of the flood control zone. For inactive, I'll say the top of that zone is 1400. And then for the top of the conservation zone, I'm going to define that by a curve as function of the date. So I think if I click off it, yeah, there it is. We can see how the top of that conservation zone, this red line here, it sort of fluctuates over the course of the year. Now, one more thing I want to do before we actually build our state variables is to define the inflow at that CP1, that upstream most junction. So let's see here, apply and OK. That closes the reservoir editor. And then this time series data set for the inflow, I still need to assign because we're going to make reference to that when we create the alternative. So that's an alternative, but I'm going to open up a HEC DSS view and then create a new DSS file. First, got to navigate to the project directory. Here we are. And then I will just call it data.dss. Okay. And I'm going to create my time series data set by going up to data, manual time series. And I can resize this dialog box right here. This particular simulation is going to be a 1-day time step instead of 1 hour. I'm just going to paste in the path name here to save me some time and then tab off. It populates the path name parts. So it's going to be CP1 flow 1 day. I don't have to populate all the fields here, but that's good enough for identifying my one and only inflow time series dataset. This is going to take place in the year 2022. I just decided that's when we're doing this. And it's going to start at the first day of the year. It'll have the units of CFS. And then for the actual flow rate values, I'll paste those in here in this value column. Okay, so I copied them onto my clipboard. And if I click Control V, I paste it in. I'll click Save. And then let's go ahead and double check that data, what it looks like. Here is the daily flows. So in the green line here, we see it starts at around 2000 CFS, and it sort of oscillates between 2000 CFS and a little over 4000 CFS over the course of the year of 2022. If we want to actually see those numbers, we can go up to File, Tabulate, and then boom, here are the actual numbers once a day. So we can, use that and reference it a little bit later when we set up the alternative. All right, back to ResSim. What I want to do next is finally create the state variables. So what we're going to be dealing with here is the water temperature. And I'm going to open up the reservoir editor, click on physical. Remember, we have 2 different gates. There's a controlled outlets. Controlled outlet group 1 is what I'm calling it at 1400 feet, which will have 1 water temperature. And controlled outlet group 2 at 50 feet above that at 1450 will have a slightly warmer water temperature. And what I want to keep track of is what is the water temperature through each of these gates, and then using a blending linear computation, determine what is the actual water temperature of the release based on not only the temperature through each of these individual gates, but also the flow rate through the gates. So that's the general direction where we're going with this particular exercise. And let's go ahead and get started. So I'm going to go edit and then click on state variables. Wait for the state variable editor to pop up here. And then let me just resize it to give myself a little bit more room. All right. So to create the state variable, I'll come to state variable, new. Then I'm going to name it temp controlled outlet 1, 1400 to more or less identify this is the temperature of the flow through the controlled outlet group 1, which has an invert of 1400. For the parameter name, I'm just going to use the same value right here. And then the parameter type, I'm going to select temperature. So if I scroll down, here is temperature right here. I also see a few other values like turbidity and pH was somewhere, which could ultimately be used for other water quality parameters. So I just wanted to point that out. Okay, so anyway, here is temperature. I also want to click this checkbox to compute as post-process. So I need to remember to do that for the other state variables that we use. And then here is the location where we type our code. We have initialization, main, and cleanup. I'm only going to be typing code in the main tab right here, which runs once every time step. And then it even gives me a little message here to add my code right here. Everything else is currently commented out in this Jython box, but there's also an example code of how to assign the value here at the end, where I set current value to this particular number, new value. What I'm going to be doing here is a little bit of typing, but for the most part, I'm going to be pasting in some code that I've already written just for the sake of time, and it helps me focus on the explanation, not so much the syntax or typing it out correctly. But what we want to do is let's start by getting the water surface elevation. And the reason we need to know the water surface elevation is because also in my data, I have a few tables here. The temperature at the water surface is going to be warmer than the temperature further down in the body of water. This table here says the difference at the water surface is 0 if the depth is 0, but as the depth increases, the water temperature also decreases as a function of that depth. And then another parameter that we're going to need is the time of year, the day of the year, because the water at the surface also changes as a function of the time of year, which ranges from 52 degrees Fahrenheit up to 76 degrees Fahrenheit. Now, these numbers I just made up, but we are going to be using them in this state variable calculation. And, whether or not they're realistic, I think they're close enough for the sake of building this particular model. Okay, so what did I say first? Water surface elevation. I'll just add a comment so I know what I'm creating here. Water surface elevation time series. And what I'm going to do is grab the model variable. So over here on the left panel, under time series, model variable, reservoir A, here is the pool elevation. So I'll just click here, pool elevation. That is all we need to do for the time series. The next row down, I'll actually get the current water surface elevation value from that time series. So to do that, I want to select the class that has that method. Let me expand the time series API class, and then there should be a method for get the current value, which is right here. Okay. And then for the parameter, what I want to paste in is this current runtime step. So just paste that in right there. And now, boom, WSEL is my current water surface elevation. Next up, I want to get the day of the year. So let's do that. Day of year is the name of the variable. This comes from the run time step class. So let me collapse the time series class. Run time step class is right here. There's get step. I'm going to use that also. I sometimes use that for debugging. And I'm looking for get HEC time. Okay, here it is. Get HEC time. Very cool. Now, the attribute from the HEC time that I want is the day of the year. So let me go up to the HEC time class, which is right here. Again, in the code, go ahead and just leave your cursor where you want the item that you select in this left panel to be inserted. And then let's scroll down to day of year, which is day of week, and day of year, double click. You can also just highlight the particular method or attribute that you want to have inserted and then click this insert into script. Works the same way as double clicking. I'm going to also just add in my step. I sometimes use this for debugging. I don't think I'm going to need it, but let's just keep it there for good measure. All right, so some more code I'm going to paste in is starting on line 25. Here we are going to calculate the surface temperature based on the day of year, the water temperature at the surface of the water, And then we can calculate the depth, which is simply the water surface elevation minus the invert to our variable here, controlled outlet 1 at 1400 feet. That's what depth is. And then using that depth, we're going to call another function that we're also going to define in just a moment called get temperature difference, which is just going to calculate the difference in temperature between the surface water and the water at that particular depth. And then ultimately, the temp at controlled outlet will give us the temperature at our controlled outlet at 1400 feet. I'm going to highlight it, copy it, and then paste it in right here because this is going to be the value that we assign to our state variable. All right, so the last thing we need to do is get these two different functions in place. We return back to my data for water temperature. Here we go. So we have the water temperature at the surface at the first day of each month. And what I've done over here in the next table over is just expanded that. So 52 for January 1st, and then you scroll down 53 for February 1st. That's the 32nd day of the year. That's the 53. And I did that for all 12 months. And I just use an equation here to do a linear interpolation. So gradually over the course of the month, the water temperature rises from January 1 to February 1, and then it increases to March 1. Eventually it peaks at August 1 and starts coming down after August. But anyway, back to the code. I'm going to just come right here and Control V to paste. This line 20 right here is a dictionary to keep track of the surface temperature. The first day of the year is 52. The second day of the year is 52.0. The third day of the year, 52.3. This is a very long line of code. So for instance, if I scrolled over, we have day 101. The water surface temperature is 59.7. Scroll over here, day 231. The water surface temperature is a nice and comfy 73.3. And then in the line below that, it's just a single line function, get surface temperature based on the day of the year, and it calls that particular dictionary. All right, so that's how that works. The next function down is to get the temperature difference. So we're passing it the depth, and if the depth is greater than 100 feet, then it's just going to return a 10-degree Fahrenheit temperature difference. We're passing in the depth in feet. We're returning the temperature difference in degrees Fahrenheit. If it's between 50 feet and 100 feet, then it's going to be a temperature difference between 7 degrees Fahrenheit and 10 degrees Fahrenheit. So anyway, I explicitly wrote out all the numbers here so you can see how that works in case you're interested in how I did it. But to sum things up, that is all we need to do for this state variable. Again, the temperature at the controlled outlet is the value that's assigned to our state variable. I'm going to go up to state variable and then save. And then I'm going to create a second state variable, which is going to be pretty much the same thing as we're seeing here, but it's going to be for our controlled outlet 2. So state variable new. This time I'm going to name it controlled outlet 2 underscore 1450. Okay. I'll use that for the parameter name, and then also a temperature and also compute as post process. This parameter name here is what will show up in part C of the DSS path once it gets written to our simulation.dss file. But I'm going to save this, return to the first state variable code, Control A, Control C, switch back to our second state variable, Control A, Control V, and the only difference I need to do is right here on what's line 51 for me, change this depth calculation to subtract the water surface elevation from 1450 instead of 1400. And that's all we need to do there. Save. Now you might be wondering, well, you wasted a bunch of lines of code for these functions that are defined twice, and that's true. And I know 3.5 does have global variables, and I just haven't experimented with them enough, but I understand that this is a little bit not best practices when it comes to writing code. All right, let's go ahead and create a alternative. And then after that, we can run the simulation and see what our state variable looks like over the course of the year of 2022. I'm going to close the state variable editor and click on alternative, edit. And now I'm going to go up to alternative, new. I'm going to give it a name. I'll just call it base. It'll be based on network 1. Okay. In the run control tab, I'll select the 1 hour time step. And then the operation set will be operation set 1. Look back. Okay, so we have a number of different parameters to put in here. The guide curve elevation starts at 1480, so I'll start that there. Further down, we need to specify the look back value for the release at each of these controlled outlets, and we're going to be starting with a balanced release allocation, which means equal flow rate through each of these two outlets. So with the initial flow of 2050, half of that would be 1025. So we'll say 1025. That 2050 just came from the inflow data. And then after that, we need to specify the uncontrolled outlet. That'll be 0 because there's 10 feet of freeboard at 1480. So no flow there. And then finally, the initial water temperature for these two outlets. The CO1 is going to be 43.3, and then CO2 is going to be 47.1. And then that's just based on all the other functions in 1480 and January 1st. All right, so one last thing, if you click on time series, click on CP1, come down here to select DSS path, and then we want to navigate to that data.dss file, select our time series dataset for the inflows that we created a long time ago, and then click on set path name, close, and alternative save. All right, let's close that and then save the network. Now let's go ahead and switch the module over to simulation mode. Simulation new, just type in sim1 and then specify the start and date time, look back date time, and end date time with the year 2022. I did this so many times prepping for this exercise. I built a macro to do it just instantly for me there. But these are the numbers that I'm using. And then select the base alternative and OK. Okay, let's go ahead and run it and see what happens. Okay, it says it's complete. I'm going to click close. Let's just take a quick look at our reservoir. Very cool. So it looks like we have plenty of capacity to maintain the guide curve elevation. If I zoom in here on the top plot here, this is the water surface elevation. We have a guide curve which fluctuates, and then since our inflow equals the release, then the pool elevation matches the guide curve elevation exactly. It's not exact because we do have a changing guide curve volume. I have to zoom in quite a bit for you to see that there's a slight shadow here where the when we have an increasing guide curve, then the inflow is going to exceed the outflow slightly, and then later in the year, the opposite is true, where the outflow exceeds the inflow just slightly. For the most part, very steady state, pretty much just a flow through model. Let's take a look at our state variables. So I'm going to open up DSS view, and I'm going to open up our RSS directory, sim1, and then simulation.dss. Okay, I'm going to sort by part B here and then scroll down to temp, which is at the bottom. And boom, here are our two state variables. Very cool. Blue is going to be the water temperature over the course of the year 2022 as it flows through controlled outlet 1 at 1400 feet. Red here is the water temperature flowing through controlled outlet 2 at 1450 feet over the course of the year 2022. So you see we have a, I don't know, 3 or 4 degree Fahrenheit difference. And of course, this is based on all the assumed input data that I provided. We can go File, Tabulate, and we can see those numbers here. It starts at about 3 degrees, 4 degrees Fahrenheit difference. Later in the middle of April, we have 50 and 54. So it's about 3.5 degrees Fahrenheit difference. Later in the year, 59.9 and 63.9, so about 4 degrees difference there. So let's close that up. One more thing I wanted to look at in ResSim is the operations. So if we plot the releases, what we have here is, like I said, an equal release of balanced release allocation between green, that is controlled outlet 1, and red, which is controlled outlet 2. It looks like there is no, down here yellow, this is the uncontrolled outlet. There's no spill over that spillway. But we could actually try to implement a little bit of spill. In fact, let's add a rule now to our reservoir operations. I'll go edit run and then reservoirs. Click on the operations tab. And then I'm going to add a minimum release rule, say min 2500. That will be from the dam. I don't want to specify one particular controlled outlet, so I'll just say dam. And then we will, release function. Okay, I said minimum, so we'll say minimum. It'll be based on a date. It's going to be constant all year long, so we'll just say 2500 and then copy that rule to all zones. I'm going to do the same thing for a max rule. I'm going to just set it to 3500, and that should create a little bit of surplus during the highest inflows. Again, dam, and then based on a date, I said maximum, and then this will just be year-round 3500, and I got to set it to all zones and apply. Okay, so let's compute that, see what the difference looks like. Hit close. Okay, thank you. Right click and let's plot the operations. Okay, cool. So we have a little bit of deviation from the guide curve, at least later in the year. I'm going to zoom in here on the elevation plot, zoom in here on the lower plot as well. Here in the lower plot, we have the inflow in black, and then we have the outflow. And you can see at 2500, there's a horizontal line at certain parts in this green line, and also at 3500, representing the maximum. And that's why in the top plot here, the top of the conservation zone, which is our guide curve, is in black, and then the actual water surface elevation here is in green. Let's take a look at the releases. Now, if I go plot releases, it looks like we have a little bit of flow from our uncontrolled outlet. So down here in yellow, we have a little bit of flow from the uncontrolled outlet. And then up at the top here, again, these are two lines on top of each other. It only looks like one line. This is controlled outlet at 1450, and this is the controlled outlet at 1400. So keep in mind, we have an equal flow rate of release from controlled outlet 1 and controlled outlet 2, which is why if we look at that DSS data again, here I'll just refresh it, even though I think the numbers are essentially the same. What I may be curious about is what is the actual temperature of the release of water downstream of the dam, which is going to be a mixing problem. And that water temperature is going to lie somewhere in between the blue line and the red line. And it's going to be a linear multiple of the two. So if all of the water was released from the controlled outlet 1 at 1400, the downstream temperature would match exactly the temperature for that controlled outlet 1. And at the same time, it would match exactly the red line if all of the release came from the controlled outlet 2 at 1,450 feet. So let's go ahead and just do the calculation right now, and then we can modify the relative flow rate between these two different outlet structures and take a look at that difference. So I'm going to close this. Let's minimize DSS view. Let's go and create a state variable, edit run state variables. Wait for the state variable editor to open up. Okay, I've got that resized. I'm going to go state variables, new. Now I'm just going to call this temp release. This is going to take into account the temperature from both controlled outlets. I'll click OK. And then for the parameter name, I will just call it temp release. This will be temperature, and again, compute as post process and Jython script. In the main tab here, this is where we want to put our code. To save time, I'm just going to paste in the code I have right here. I have some debugging code that we don't need, so I'll just take that out. Let me scroll over here to the left. There we go. All right, so real quick, what we're doing is we're getting the flow rate out of controlled outlet 1 at 1400. We're getting the flow rate right here out of controlled outlet 2 at 1450. The sum is just those two added together. And then right here on line 28 and 31, this is the temperature from controlled outlet 1 and controlled outlet 2. And what we're doing is basically just getting the state variable. So we can access that by coming up here, double clicking on the state variable, and then that block of code gets inserted right here, and we're getting the value. And then finally, this temp release state variable is assigned this value, temp release, which is what we're calculating on line 34. And again, we're just doing a linear combination of the temperature from each of those controlled outlets based on the flow rate through those outlets too. In fact, the actual quantity isn't important, but rather the proportion is. That's why we're dividing by the total flow over here as our denominator. So the flow rate through CO1 times the temperature through CO1 plus the flow rate through CO2 times the temperature through CO2, and then all divided by the total flow rate through both controlled outlet 1 and controlled outlet 2. All right, so let's see if that works. State variable and save. I'll go ahead and close that, and let's compute once again. Okay, that looks good. I'm going to go straight to DSS view this time. Click on view, refresh. Now we have our third state variable right here. I'm going to highlight and view all three at the same time. And very cool. It looks like they all came in. I'm going to zoom in real quick. And this third and new state variable, this third series of data here, represents the temperature of the water released from the reservoir from the controlled outlet 1 and controlled outlet 2. Now, you may be thinking to yourself, what about that small amount of spill from the uncontrolled outlet? And you got me there. I did not include that in this particular calculation, but you can see that with equal flow through both CO1 and CO2, which is from blue and red, respectively, Then the green line here splits the difference. So this is basically 50% vertical between the two. But say, for instance, that we limited the flow through controlled outlet 1, so more flow was going through controlled outlet 2. That means the downstream release from the entire reservoir would be warmer water. The green line would move closer to the red line. So let's go ahead and demonstrate that one last time, and then we'll call it good, just to show how that relationship would work. So I'm going to close this, minimize that. And then let's see, there's a lot of different ways we could do this. We could change the release allocation. I'm going to go ahead and just add a new rule to the reservoir. So edit run, reservoirs, right click, add new rule. I'm going to call this CO1 1400, and then I'll just say 1000 CFS. So I'm going to just set the release at 1000 CFS. Or actually, let's make it a little bit higher. Let's make it, how about 2000 CFS? That should be interesting because, yeah, that would look good. I'm going to set this to controlled outlet 1. Of course, that's what I named it. Release function. Okay. This is going to be a specified release. That's why it's down here in the bottom of the rule zone tree. Typically, your specified releases would have the lower priority, and it'll be based on a date. It'll be year round, and I'm going to say 2000 CFS, and then copy that to all the zones. So add rule to all zones, apply, okay, and compute. Oh, okay, so I did see one warning there. The warning is that I need to update the look back data for our new state variable temp release. So let's go ahead and do that, and then we shouldn't get that warning again. I'm going to click on alternative editor, look back, and then this value here is going to be between 43 and 47. I believe it's going to be closer to 43 though. So let's just say it's 43.5 and then save. It'll correct itself anyway. All right. Okay. And compute. We shouldn't have that warning, and I don't see it. So we're good there. Okay. Let's go ahead and take a look at the releases now. Okay. I sort of did the opposite of what I said I was going to do. So now we have more flow coming out of CO1, a constant 2000. It's this green line. And then through CO2, controlled outlet 2 at 1450, we have less flow. When the release from controlled outlet 2 is down here at 500, we're going to have 4 times more flow out of controlled outlet 1, which means the temperature is going to be 80% of the temperature at controlled outlet 1, 1400, as opposed to what it is at 1450. However, in, say, February and March, when we're maxing out our total release from the dam at 3500, we have, again, 2,000 out of CO1, but 1,500 out of CO2. And in that situation, I expect the temperature to be much closer to splitting the difference between the temperatures at those two elevations, 1,400 and 1,450. So let's go ahead and take a look at that. Let's analyze the first few months of our temperature release from the dam data. We'll close this. Let's go to DSS view one last time. View, refresh the catalog, scroll down here, open it up. I'm going to zoom in here on the first couple months. And just like I suggested, what we have is the green line here, which is the total, the temperature release from the dam is much closer to the blue line than the red line. Blue being the 1400, red being the controlled outlet 2 at 1450. But then later, so like maybe in March, late February, early March, the green line here representing the total temperature almost splits the difference. It would be a ratio of 4 to 3 as opposed to 4 to 1 like we had at the beginning of the year near January, right? So anyway, this is just a quick reminder of one more example of how to use ResSim and state variables. In this situation, what we did was we created the water temperature profile over the course of the year, and we calculated what the water temperature was based on all of our assumptions of historical data and depth gradient temperature changes, and of course the inflow and the guide curve to give us a lot of analysis, which was easy to do using state variables in ResSim.